In this video, we're going to talk about programs themselves, what they are, processors, and languages. All right, so first off, a program is just a collection of instructions that perform some job when executed by the computer. And most programs are usually written by a programmer in some programming language. In this class, we're looking at Java as the language. And then the instructions in a program are carried out by the processor, also called the central processing unit, or CPU, but I usually just call it a processor for short. So this is what a typical processor looks like. Inside, it's really just a bunch of circuits in there, essentially, or that's one way you can think about it. And it's kind of like the brain of the computer. So inside, that's what it looks like. And then there's a cover that fits over it. So if you take off the cover and look inside, it'll look like this. So that's what a processor looks like. And then a processor sits inside a motherboard. You can see right here, if you look, this little thing that looks like a square, that's where the chip sits in there. This little kind of cover thing opens up and you seat the chip down in there and then close it back up. And so that's where the chip would sit, right in here. And then here's a picture of a motherboard that's inside the case, right? And if you haven't ever cracked open a computer and looked in what's inside, that's kind of how it sits in there, inside of a case. And here the chip would be underneath this fan right here on the motherboard. So here's the motherboard, and that chip is down underneath the fan. The chip, when you carry out instructions, it generates heat, and so it needs to be cooled off. If not, then it's not good for the chip. So this little fan right here is just a cooling system, and that chip is actually underneath that fan. All right, so that's what actually carries out the instructions that you set into the computer with your program. So the thing about the processor that you need to understand is that the processor only understands instructions that are written in machine language, and machine language instructions consist entirely of sequences of zeros and ones. So here are just some examples of command that you might see in machine language. Nothing but zeros and ones like that. Okay, and the chip doesn't really understand anything else other than that. And the reason why is because, well, that's easier for engineers and chip designers to implement inside the computer. That language is of zeros and ones. Okay, so this is the only language that the chip will understand. Over here, you'll see some hexadecimal instructions. These are numbers written in base 16. Base 16 uses the 0 through 9 digits, just like our base 10 system does. And it also uses A, B, C, D, E, and F, the letters in the English language, as extra digits in their number system. So. And base 16 just allows a more compact way of writing these machine language instructions. It's a little bit easier for humans to look at this rather than this over here. All right, so low-level languages are languages that are designed with a computer in mind. So an example would be a machine language that we just looked at. And a couple of other examples, assembly language and bytecode. And bytecode is actually from Java. The thing about low-level languages is that they are usually hardware dependent. It depends on what kind of computer you're running them on. They're different, for different types of hardware. Okay. And so down here at the bottom, you can see an example of assembly language code, or kind of what assembly language code looks like. And you can see it's a little more friendly towards for humans instead of a bunch of zeros and ones, then you can the commands have little um, keywords, move, add, and so on and so forth. So this is a little bit easier for humans to read. And again, one of the issues with low-level languages, it kind of depends on what kind of hardware you have. Maybe you have one type of computer and it has its own machine language, whereas if you buy a different type of computer, it has a different machine language. These days, it's really not so much like that. It's a little more standardized than it used to be, but it can still be that way, where if you have two different types of machines, then they have two different types of machine language or assembly language. All right, and that would be a problem, if you were a software developer and wanted to develop something that can be run on a lot of different machines. As opposed to low-level languages, you have high-level languages. When high-level languages are languages with designed with, it says with a computer in mind, but that's a typo. It should say humans in mind. There. Examples are Java and lots of other computer languages you might have heard about: COBOL, Ruby, Python, C, C++, and so on. So the issue then is if the processor only understands machine language, that's difficult for humans to deal with all the time. So we have these high-level languages. They're easier for humans to deal with. But the issue is, in order to get your program to run, then high-level languages or instructions in high-level languages need to be translated into machine language before the program can be run. Okay, so another definition here: source code. That's defined as the high-level language instructions written by the programmer. And your source code is translated into machine language by another program, and that program is usually called a compiler or interpreter for the most part. There are other things as well, but these are the only two that we're going to talk about right now. So a compiler and an interpreter are different from each other. What's the difference? A compiler translates the entire source code at one single time and then ships the translation, the machine language instructions, off to the processor to do it. So that's similar to how somebody would translate a book from one natural language into another. They take the book and then they do the translation, and then they put the translation out there for people to read. An interpreter, on the other hand, translates the source code line by line, alternating between translating a line and then shipping those machine language translations off to the processor. It's not exactly line by line, but it doesn't hurt at this level to think about it that way. This is a lot like watching an interview with somebody on TV who doesn't speak the language, and so what of the interviewer, somebody being interviewed by somebody and they speak two different languages. So what will happen is that the interviewer will ask a question, the translator will translate that sentence and then wait, for the reply and then translate that back. So it's a little like that. You translate sentence by sentence or response by response instead of translating everything at once. So that's the difference between a compiler and an interpreter. So now that we know about machine language and high-level languages being translated by a compiler or interpreter, it's now time to talk about the process specific to Java. A lot of languages, you either use one or the other. You either use a compiler or an interpreter, and sometimes a language you can use either one or the other, but generally speaking, most people use either a compiler or interpreter or an interpreter. So, but Java has basically a two-step compilation process. So Java is compiled into an intermediate language called bytecode. So I'm just going to close this out for a second. So here's the program that I have. This is my source code right here. And I'm going to click the green plus here to compile my program. And when I do that, it's going to generate this other file over here, right? Hello world.class, and that file is actually the bytecode file. So that's a lower level language. It's been translated by the compiler into this bytecode right here. So that's what we're talking about. All right. Once that happens, right, then the bytecode is interpreted by a program called the Java Virtual Machine, abbreviated JVM. Okay. So when you go to run the program, now there's another program that looks at the bytecode file here and interprets that file and then runs your program. So there is a two-step process in Java. Many other languages, don't have two steps, either compile or interpret, and that's it. So it's a little unusual if you're used to some other languages where you just compile only or interpret only. So the question then is, why does Java do it that way? Well, they do it that way because the two-step compilation process leads to increased portability. In other words, you can write your program once, right, and then run it anywhere. So a program it allows for programs to be run on more machines without having to change a lot of stuff drastically. So you can run your program on many different types of machines without decreasing performance. So interpreted programs are similar to that, where they can be run on lots of different platforms or machines, but there's a performance decrease because of that, because you're doing the translation a little bit at a time. So this is kind of a Java's way of taking a happy in-between place where they can increase portability and then not take such a performance hit as just relying solely on interpreted programs. All right, and that's it.